Hello everyone and welcome to another episode on complete reference to CUDA programming. Here I'll discuss what are the topics that I'm going to cover throughout this course. Some topics are going to be fundamental, some topics are going to be intermediate, and finally some topics belong to advanced optimization techniques in CUDA programming. So in first few sessions, we'll talk about introduction to parallel computing and how it is different from sequential computing. So once we understand what's the major difference between sequential and parallel computing, we'll try to understand over the last 4 or 5 decades what are the advancements that are happened in the CPU architectures. We'll see what are the limitations of these CPU architectures as well and why we are shifting from multi-core CPU architectures to GPU. We'll also see some performance metrics and this includes speed up, then efficiency, scalability, etc. Whenever we talk about parallel computing, it is very important to measure the performance of your parallel program because ultimately our aim is to reduce the time required to perform that computation. And how we measure that performance improvements by using different metrics, right? So maybe speed up is one of them. Then we'll talk about efficiency, how effectively or efficiently your hardware is being utilized. Then we can also talk about the scalability, that means in terms of your increase in number of resources, how your program is behaving, right? So these are the some performance metrics we'll be able to understand in this course. Next, we'll see what are the limitations of multi-core CPUs, right? So why we are moving from multi-core CPU to basically a GPU. Before that, we'll understand what's the major difference between CPU architecture and GPU architecture. So often we say that CPU is a latency oriented device and GPU is a throughput oriented device. So we'll try to understand what's the major difference between these two architectures. Then we'll focus on a very fundamental concept in CUDA programming, that is what is GPU architecture, right? So we'll try to understand in depth how the number of computing resources and memory is organized on this GPU. Then we'll start with our first CUDA program. Syntactically, we'll try to understand how CUDA program can be written and how your simple C or C++ code can be converted into a CUDA program. Here, we'll focus only syntactically, what are the things you have to add in your existing C program so that it can be converted into C program to a CUDA program. Then we understand complete execution, CUDA program execution model on the GPU. What are the steps we have to follow in order to convert a sequential program into a CUDA program that will be executed on GPU. Then a very important topic, or we can say a crux of this CUDA programming, is nothing but your thread organization. So basically in CUDA programming, what we are going to do, we are going to create n number of threads, and these threads will be assigned a different task and they can execute in parallel. So that is the whole idea behind this CUDA programming. Now all these tasks can be performed by your threads, and threads can be organized in 1D, 2D or 3D fashion. So first we'll understand what is this 1D thread organization, what are the different parameters are associated with these threads, that we'll try to understand. Later on, we'll take some case studies. We'll take simple vector addition program and we'll try to understand this 1D thread organization. Then some concepts like local to global thread mapping, then handling input size and number of thread mismatch, that we'll try to understand in this session. Similarly, once we get familiar with this 1D thread organization, we'll extend this concept on 2-dimension and 3-dimension. So basically, we arrange these threads in 2D and 3D if we are having a data structure which is of 2 or 3 dimension, right? So for example, if you want to work on 1-dimensional array or a vector, we can organize our threads into 1D format. But let's say if you are working on higher dimensional data structure such as matrix or tensor or 3-dimensional tensor, then it is better to organize our threads into 2D or 3D format so that we can have easily mapping between data and the threads. So for that, we'll take some case studies to demonstrate this 2D and 3D thread organization, and we'll take some case studies such as matrix addition and matrix multiplications. Now, after that, after the in-depth understanding of 2D and 3D organization, we will move towards this memory organization. It is very important to understand the memory organization if you are writing any program. For example, if you are writing C program, C++ program, you must be familiar with the concept of RAM, cache memory, then register memory. So these are the memories that are present on CPU side. Similarly, on GPU, we'll be having another type of memories like global memory, constant memory, shared memory, texture memory, etc., or register memory. And effective utilization of these memories is going to promise us a better performance. So it is very important to understand all the type of memories on the GPU. Then we have another session on visual and command line profiling. So basically profiling is going to give you hotspot where the parallelization is required, where what are the limitations of your parallel execution that we can observe by means of command line or visual profiling. So that can be done using command line and visual profiling. We'll try to understand the behavior of unified memory, and for that we'll also use this command line and visual profiling. So basically unified memory is very important concept that is introduced after CUDA version 6.0, where we get the illusion as a programmer that there is no distinct memory between CPU and GPU, and we can access the memory from CPU as well as GPU without having explicit data transfer. So again, very elegant concept, that is unified memory, and for that we'll be dedicating at least 2-3 sessions, and practically we'll try to understand the behavior of this unified memory, and in what case it is advised to use this unified memory and where to avoid this usage of unified memory. That also can be discussed in these sessions. Then the most important topic or memory in case of CUDA programming is utilization of the shared memory, which will improve the performance of your code by reducing the number of memory footprints on the global memory. So just like on your CPU side, when data is placed in cache memory, it will reduce your main memory transactions, and the required data can be easily accessed or efficiently accessed from the cache memory without accessing the main memory. So if you store the data in cache memory, then obviously you don't have to access main memory, and which will increase the performance by reducing the main memory access transactions. So same concept is applied here in case of shared memory. We'll see how this shared memory is organized and how it can be accessed, and to demonstrate that we will take a very important case study, that is convolution operation. So this convolution operation is used in various fields of science and engineering. If you talk about deep learning, where convolution operation is very prominent, then in case of image processing, then convolution operation is also used to perform different types of image enhancement techniques. In case of fluid dynamics also, the data structure is going to be a 3-dimension, and where also the similar computing pattern can be observed. So for that reason, we'll try to understand this 1D and 2D convolution using shared memory and without using shared memory, and how it impact the performance. Finally, we'll also discuss very important case study, that is matrix multiplication, which is again a very basic computation in various fields of science and engineering. We'll also demonstrate importance of the shared memory by using this matrix multiplication using and without using shared memory, and what is the performance difference between these two. From this session onwards, we'll be talking about some advanced concepts in CUDA programming, which will help us to improve the performance even further level. So one of them is global memory coalescing. So if in case of your threads accessing memory in coalesced fashion, how it will impact the performance, that will be demonstrated using different case studies like reduction and matrix addition using coalesced memory access pattern. After that, we have one more important concept in CUDA programming, is that CUDA streams, where we can launch multiple CUDA kernels that can be executed in parallel. So One way we can achieve the parallelism inside the CUDA function, and other way of parallelization is across the CUDA functions, right? So we'll try to focus on this across the kernel parallelization using these CUDA streams. These CUDA streams are again useful when you want to overlap the data transfer and the compute. So for that reason also we can make use of this CUDA stream, so that it will ensure the effective utilization of your GPU resources. We'll try to understand this CUDA stream behavior again by means of visual profiling. Then few topics like what is CUDA warps and occupancy, what are the limitations of usage of this on-chip resources, and how it will affect the occupancy of your GPU. That we'll try to understand in later sessions. And finally, we'll be having summary of the entire course, and we'll conclude this course. So these are the topic I'm going to cover throughout this series. And of course, as of now, I have recorded this video. I have these topics in my mind, but definitely I'll be adding few more topics and few more exercise problems in the subsequent sessions. So thank you all, and let's meet in the next session where we'll talk about the first topic, that is introduction to parallel computing and how it is different from sequential computing.